Okay, I think we can start now. So good morning, good afternoon, and good evening, everyone.
Andres,
So
let's give it 2 more minutes until the hour.
Sorry?
Let's give it 2 more minutes until the hour.
Ah, okay.
Many people connect.
Oh, no, it's, okay, I see. It's just before 3 p.m. local time. Okay.
Okay, now we can probably get going, Andres, if you want to kick things off.
Okay, great. Okay, so good morning and good afternoon and good evening for everyone. So now it's time to talk a little bit about TESS and solar system. Just a couple of words as a kind of introduction. So when we are writing some paper or submitting a proposal or something similar, we always start this kind of introduction to TESS and solar system in a way that, okay, in the primary mission, TESS avoids the ecliptic plane by ±6 degrees, but, and the emphasis is on but, because the scale height of the solar system is quite big. If you just think about the main belt, asteroid, and the Kuiper belt object, and especially nearby objects like NEOs, that there is a really many of solar system objects which are passing by in the field of view of TESS, especially in camera 1. If you just take a quick look on the TESS field of view maps. So there is a very high and very nice opportunity in TESS to do solar system science. So when we were just discussing about this panel and this section, we tried to cover all of the aspects which can be interesting for scientists working in solar system stuff and basically for everyone else, covering objects from the very near objects which can treat Earth up to the Kuiper belt, including and in between minor planets, main belt asteroids, Trojans, everything. And we also deal with 2 aspects mainly. The first is discovery, so detecting new objects, and the second is the characterization of known objects. So these are somehow 2 distinct topics which can be covered by TESS, and both are very interesting. So in the first part of this section, we will have the panel, and we will have 4 short talks, after which we can discuss some issues, and we also weigh the questions on the Slack channel, which is named Solar System, of course. And so feel free to ask questions related to the talks and in general to solar system science, and we try to answer it and discuss it. So we have 4 presenters: Christina Hedges from NASA Ames, Matt Payne from Minor Planet Center, he's acting director, Róbert Szakáts from Concolly Observatory, and Deb Woods from Lincoln Laboratory, MIT. So I would like to ask first, so let's do it in a way how the videos are in the YouTube channel of the conference and also in the official schedule. So first I would like to ask Christina, and then Matt, and then Robert, and then Deb for their, I would say, 4, 5, 6 minute long introductions. And of course, in the YouTube channel, you can find the more detailed versions of this presentation. So feel free to watch it, and then we can have the discussion and the questions. So, Christina.
Hi, everyone. Thanks, Avi. So my name is Christina Hedges, and yeah, I work at NASA Ames, and I have a small group at NASA Ames, and we're focused on detecting solar system objects in TESS. In the full talk that's available on YouTube, I go through these slides at a little bit of a slower pace, but I'm going to give you the sort of overview, the trailer, if you like, for the talk that's on the YouTube channel. In this talk, I'm talking mostly about what we can achieve with TESS for solar system objects, which is what we're focused on in my group at Ames. And in this talk, I show you a few of the things that we've been working on, including tools for you to get access to the data products. I'm going to talk about how TESS is very, very unique. Let's see if I'm going to skip forward a few slides. This is where I want to take you guys. One of the tools that I talk about in this talk and I'd like to let you guys know about is called TESS Backdrop. We've been developing tools so that you guys can get access to solar system objects and so that we can get access to them so that we can better understand the light curves of these objects. The light curves of solar system objects tell us about the rotation of asteroids. They tell us about eclipses and eclipses between binary objects, tell us about all sorts about the asteroids. And so we're developing a lot of tools so that everyone can get access to them, be it community or us in our sort of funded science work. One of the tools that we've been developing so that people can get access to this is TESS Backdrop. This is a tool to really quickly get rid of the TESS scattered light. I think we're on Friday now, so everybody knows that TESS is fantastic. Everybody knows that TESS has good baseline, it's precise, it's all sky. So this is a great resource for solar system objects, but also we know that there is this scattered light, this background that's going to get in the way of our understanding of faint objects. TESS is going to see, or has seen, about 50,000 main belt asteroids brighter than 19th, brighter than 20th in the first cycle. And so there's a wealth of this information, but to get access to it, we really need to get rid of this scattered light. So one of the tools we've been developing is TESS Backdrop. TESS Backdrop will really quickly let you correct any pixel in the data set. This is under development, and currently we're working on the infrastructure and doing a few runs on the supercomputer to enable you to do this really fast. The idea is we create a model which is made up of lots of polynomials. Those polynomials have optimum weights, and then we deliver these weight files to the community, and you can use those weight files to make beautiful beautiful background models like this one here, which corrects out scattered light. As I said, this is under development, and so you can check us out online. The idea is that you would be able to create a TESS Backdrop object and then pass in a TPF, and it'll correct it for you in milliseconds. This should be useful for astrophysics or planetary science, but it's hopefully going to make it so that we can get access to all these light curves without the TESS scattered light. We've also been developing a tool called TESS Cloud. TESS Cloud will allow you to get access to the FFIs and get access to moving objects through the TESS data set that's on Amazon, the Amazon Cloud Service. You can already import TESS Cloud. You can already use this, and you can cut out asteroids. You can use it to cut out, for example, Vesta, and it will give you moving target pixel files focused on asteroids. We're still improving some of these tools, but this one absolutely works. You can install it today and get access to the data through the cloud very, very quickly. Here's an example of one of those moving objects. This is Apophis. Apophis is moving extremely fast because it's quite close to the Earth. And so you can see it moving in the middle of the frame. There's actually sky scattered light coming in. That's why there was a black frame. But you can see it moving relative to the stars in the background. I'm going to switch slides here. My group's also been working on astrometry, and that sort of falls into two camps, accuracy and precision. We're able to get pretty good accuracy from TESS. We're able to get, for targets that we've tested, within a quarter of a pixel for most individual cadences from what JPL suggests from small bodies is the center of the asteroid. And so we're able to get fairly good accuracy. We're going to be writing up our investigation into the TESS accuracy along with the TESS precision very, very soon. But we are able to get within a quarter of a pixel of what is expected, which is really great. Also able to do really, really well on the precision. This is work that Rob Morris at NASA Ames has been pioneering. We've been using PSF fitting to get the flux and the centroids of asteroids. And so the topic of this talk was, what can TESS do for asteroids? Certainly in this talk I go through, we can get flux, we can get light curves, we can do good rotation rates. One of the things that we can do using PSF fitting is we can get really, really precise centroids for these asteroids. We can get precise astrometry. On the screen, I'm showing you this is for Apophis using our PSF centroiding technique. We have removed the accuracy part of this. This is compared to like a smooth polynomial. But as you've seen from the previous slide, we can do fairly well on accuracy compared to JPL Small Bodies Horizons service. You can see that we're getting to well within a quarter of an arc second, bearing in mind that TESS pixels are 21 arc seconds across. This is really, really excellent. Of the centroids that we expect for Apophis in column and row, in the column and row direction of the spacecraft, but this is in arc seconds. So we're getting really, really precise astrometry for objects like Apophis. The nice thing about our PSF method is that we also get flux for free. And so this is the light curve for Apophis in TESS. You can see the rotation modulation, and you can see we're getting a really, really, really precise light curve here. So we're excited to keep mining and developing these tools and hopefully get some PSF tools as well available for the public. This is all based on work that the Spock have pioneered. So this is currently not a publicly accessible tool, but it is a goal that we can get these tools together so that we can deliver them to the community. I'm going to skip ahead again because I only have a few moments. And I'm going to show you, I'll answer that question, what is the limit with TESS? The limit with TESS that we believe we'll be able to probe with our investigation is 22nd. But at 22nd, we may be doing very, very coarse photometry. So we still need to answer this question in detail. How faint can TESS go? But we believe that in our catalog, we'll be able to get down to about 22nd magnitude with very coarse photometry. The other part that I'd like to see, to show you, which is what we can do with TESS. These are just some example objects from TESS Sector 2. The two objects are in regular time on the top, and then they've been followed on the bottom. What's going on here is that we've got binary asteroids. As binary asteroids are eclipsing. TESS can be fantastic for understanding the binarity of these eclipsing objects. The team at NASA Ames, we have a lot of heritage from working with Kepler, a lot of heritage making open source tools. And so the plan at the moment is to take some of the open source astrophysics tools for understanding transits and eclipses and use them to build a suite of tools that will help us fit and find these eclipsing objects and measure them and get good population statistics for objects that eclipse like this. As you can see, these are very, very similar to some of the features of eclipsing binaries. And so we're going to be developing those tools as we move forward. And so hopefully TESS will help us understand binarity as well. I'm going to call it there because I think that was my fair shake at 6 minutes. I think questions at the end, or questions now?
Okay, thank you very much. It was really, really nice. I really like the technique what you did on Apophis. So
Yeah.
this is something what we really need to discuss in the future.
Okay.
Okay, so Matt, please.
All right, thank you. Okay, so thanks very much, everyone. So my name is Matthew Payne. I'm the acting director of the Minor Planets Center. And so my talk is on a test search for distant solar system planets or objects in general. So the sort of things that I'm interested in trying to use TESS to find are distant objects in and around the ice giants and outwards. So things like centaurs and scattered disk objects, which are on highly eccentric orbits, and things like Kuiper belt objects, as well as more distant objects, such as some detached objects like Sedna, comets, and then possibly something like Planet 9 if it happens to exist. So the basic approach to doing this is to use a shift and stack technique to search for unknown objects. So the idea is that you have a full sector's worth of TESS FFI data, and some unknown object could be going across the field of view in pretty much any direction, moving at almost any rate. So what we want to do is to shift and stack the data. So the object is going to appear at different locations across the field of view during the course of a sector. So we want to take the data from each of those exposures, shift them at different rates so that we're trying to stack up the flux so that we can go well below the single exposure detection limit, stack all of that data up and try and detect really faint objects. Now, in order to do this, because the orbit of the objects that you're looking for is unknown, we're trying to detect new objects, you've got to try lots of different orbits, lots of different rates, lots of different orientations. So it then becomes a computational challenge to understand how much computation do you need to put into search across a whole suite of different orbits to be able to efficiently find and characterize your rates of discovery. And so lots of the details of that are in the main talk. But putting all of that together, a sort of a rough estimate is that depending on the levels of background light, whether it's zodiacal light, stellar flux, etc. So the different areas of the sky give you different detection efficiencies. But so nominally, we think we can get down to 20-second magnitude by stacking up data. So we should be able to detect and discover 20-second magnitude objects like, as a fairly general average. In some areas of the sky, it might be a little worse than that, but in some areas of the sky, it's definitely going to be better than that. And so as just a sort of like proof of principle of this, here's some known objects. So these are not discovering unknown things, but for some known objects, there's some examples here where you're going down to 21.6, and the data has been shifted here and stacked up, and you can very, very, very clearly and easily detect these objects. And so myself, Matt Holman, and Andreas looked at this like a year or two ago, and I'm working with a postdoc, Mike Alexanderson, to set up a lot of the infrastructure to do this for unknown objects at the moment. And Malena Rice, who's going to give a talk later, has also published work on this idea, and again, detecting some known objects and showing that this is like easily doable. And then to give you an idea of what that means, so if we can go ahead and discover objects in the outer solar system down to like 20-second magnitude, then in the Kuiper belt, we already know of about 1,200 objects. And so detectable, we think that TESS can probably detect about 1,400. This should say 1,400, not 1,200. So there should be around about a couple of hundred new TNOs that can be discovered by TESS. So you're adding a little bit to our knowledge of the Kuiper belt objects. But perhaps more importantly, For the much more highly scattered objects like centaurs and the scattered disk objects, which have a much larger scale height, as Andras was mentioning earlier on, then at the moment we probably only know around about 800 such objects, and TESS has the ability to probably detect somewhere in the region of 1600 or so objects. So we're basically approximately doubling the known population of those objects if we can go ahead and find all of these. And so what I'm been working on, or in particular Mike Alexanderson has been working on, is like shift and stack software to do this. So the idea is to make sort of simple to use software. So I'm just sort of highlighting here, just in around about half a dozen lines of code. You can load up a whole bunch of data. And then here I'm illustrating doing shift and stack for a named object. So you can just hand it the name and it understands all of the background work that has to be done, work out where the object should be, go and shift and stack the data and pull it out and make the plots that you can see down here at the bottom as simple illustrations. And so I'm sort of emphasizing here that this code is sort of very generally applicable. Actually, here I'm using some hypersuprime cam data to illustrate that this code is going to be completely generally available, will work with any observatory, ground-based or space-based, and to allow the community to do shift and stack searches using a whole range, a whole combination of different data sets. So just as a quick summary, we're primarily focused on using shift and stack to search test data to find outer solar system objects. We're writing and releasing this software to do so. And then as a sideline, we're also interested in trying to use the same technique, but to discover different sets of objects that move a lot faster. So they're harder to find in some respects, but things like interstellar comets, like the recently sort of discovered comet Borisov is very bright. And so you don't need to stack very much data. So finding them looks like it can be plausible using this approach as well. Okay, so I'll stop there. Thank you.
Okay, thank you very much, Matt. It was really, really nice. And still there's a lot of questions. We start to get a few questions on Slack, so we can just proceed to the questions after, I think, Robert's talk. So, Robert, let's hope that everything will work. So, yeah.
Okay. So I'm Róbert Szakáts. I work at the Konkoly Observatory in Budapest, and I will summarize my presentation in a few slides. So as we can see, TESS avoids the ecliptic plane, but regardless of this, we can observe a lot of asteroids with this space telescope. And also, as we saw, we have to process the raw images to have good enough photometry at the end. I will not go into details with the steps, but we have to remove the background, the scatter light. Also, after we did some image subtraction with some median images, and at the end we had only mostly only the targets or the moving objects on these images, and after that we can do the photometry on them. Of course, our method works only for known solar system objects. We are not trying to discover new objects right now, but as we saw in other presentations, it's a possibility. So here is a really nice example light curve. Of course, it's a very bright asteroid. You can see the folded light curve here with the binned points. It's a really nice one. As we saw, the limit for these solar system objects in our case with this method was around 90 magnitudes. We managed to extract acceptable light curves around that magnitude, but at the end we we did not cover the fainter objects. So basically, we processed the first year. From that, only the camera 1 data, which is the closest to the ecliptic plane. And we try to find the known asteroids and do photometry on them. At the end, we had almost 10,000 light curves of solar system objects. And we released the data release of this. It's the TESS solar system data release 1 for year 1. What we can do with this data? Well, first we can compare it to known databases. Here it's a comparison for the Minor Planet Center's light curve database, and you can see that 80% of our selected asteroids and the asteroids from the light curve database has the same period. So it looks good. Of course, we have to, and we cannot use all the 10,000 asteroids for this purpose. We selected the common ones from the light curve database and from the TESS that has accurate and good defined period and amplitude in the light curve database. So it was around 10,000 objects. So that's what you can see here. Also, you can see that TESS detected longer periods for around 8% of these objects. This is because, of course, that TESS could observe for almost for a month one area, and a lot of the asteroids we observed were on the CCD for many weeks. So we could detect, of course, longer periods in this case. Also, here is the histogram of these asteroids. Here we can see some K2 asteroids. This is the Minor Planet Center's light curve database, and this is the TESS data. Here also we can see that we detected more longer period asteroids. If you do a peak-to-peak amplitude and period diagram with the log-log scale, the colors here are representing the number of objects. We can see that there is a peak around 4-6 hours, which is I think well known for most of the asteroids. But the interesting part is that there is a second peak here in a much larger period, around 18 or 20 hours. So that is a very good question, that what kind of asteroids are here in this, well, let's say second, around this second peak here. Of course, besides of some statistical analysis, you can look at individual asteroid light curves. Here I took some examples from a recent paper. In this paper, the authors tried to obtain physical and thermophysical properties of slowly rotating asteroids. And for this, in some cases, they used TESS data. Here also we can see the folded light curves. They are both slowly rotating longer period asteroids. And the TESS data clearly helped in this paper to model the shape and size of the asteroid. And of course, with the help of infrared data, the thermophysical properties also could be modeled here. Another example with K2 data. Here, 2 asteroid families were studied, Jovian Trojans and Hildas, and you can see that there is a double peak in the rotation rate. and the second group of these asteroids looked a little bit off from the main group. But if you do a median analysis of the periods, you can see that the median periods of these asteroids are closer than the rates that TESS observed for main belt asteroids here. Okay, and of course, with the synergy with other telescopes or other data like infrared data, we can do a lot. In the future, we are planning to release the data release 2 that will include light curves and data for year 1, year 2, and for the year 3 fields. And we know that in year 4, in fact, right now, TESS will observe the ecliptic plane 2 in sectors 42 to 46, and it will cover 2/3 of the ecliptic plane by the end, and we are expecting tens of thousands of solar system objects in these frames, and we will have an extraordinary amount of data to process, a lot of light curves, a lot of data from this. Of course, in the long run, these homogeneous observations with TESS will allow us to do shape modeling for the asteroids that were shown in different sectors, and we can expand the data with a lot of slow rotators, binary tumblers, and so on. I think we will have a lot of light curves for asteroids that don't have period or amplitude information right now. Thank you.
Thank you, Robbie. We got a question which I think that would be the best to answer now. Can you go back to your slide with where on the right there is the heat map, and on the left there is the distribution of the periods? And George is asking that what are those 3 curves? Yes, here.
Yeah.
Because I think you either didn't tell or was just too quick, because I also don't really remember. So the blue, red, and black.
Blue, red, and black.
No, on the left.
Sorry. Yeah, the blue is Kepler data from K2. The red is the asteroid, the light curve database from Minor Planet Center and the black is from the TESS data release 1 that we did.
Okay.
So this is the histogram of the periods, basically.
Okay, thank you. Yeah, okay. So I think then we can just go for the last summary. Deb?
Okay. All right.
Okay, it's there working. Okay.
Great, thank you. I'm Deb Woods. I'm a researcher at MIT Lincoln Laboratory, and I'll be talking about TESS asteroid observations, focusing on our detection processing pipeline. As everyone is aware, TESS has a very wide field of view, which is one of its strengths as an asteroid detection system. And so I'm using TESS for the purpose of asteroid discovery. And TESS has a very valuable role to play in asteroid discovery. Shown on the left is the sky coverage for TESS. This is during year 3. It looks the same for year 1. And shown on the right is the sky coverage for all major asteroid search sensors that are contributing to the Minor Planet Center, who collects the asteroid observations for all the major sensors. And so, as you can see, there's really complementary sky coverage, particularly in the southern hemisphere. And so TESS has a role as an asteroid search sensor. While it doesn't go as faint as some of the major sensors like Catalina or Pan-STARRS, it offers an opportunity for sky coverage where those do not. So our program is a contributing sensor funded by the NASA Near Earth Object Observations Office, which is part of the Planetary Defense Coordination Office. And so the goal of our program is asteroid discovery, particularly for near Earth objects. So in my brief intro here, I'm just going to focus on how are we getting the asteroid data out of the TESS images, because again, these are without a priori information. So I'm just going to touch on some of the highlights in this short intro, but there are more details in my full talk, and then there's the reference I'll send at the end for our recent publication. So in order to find the moving objects, of course, we have to get rid of the clutter, which for our case is all the stars and other objects in the background. So shown here is just a little cutout from 1CCD, the same region, same pixels shown in the original image. This is an original minus the median. And then this is what comes out of our pipeline, original minus the median divided by standard eclipse standard deviation. We have some field flattening. Again, lots of details in my paper for exactly how are we generating the difference images, which we use to do our detections in. And so we try to get the cleanest images possible, of course, to push as faint as possible, barely above the noise. So just another highlight from our work, looking at the astrometric residuals. So how well are we able to do the astrometry? And so this plot includes both the accuracy of the plate solution and the precision of the centroiding. So for the astrometry, we're using FIT-SH methods that are published by Andras, and we have really good results. For bright objects, we show median less than 1 arcsecond, which is a 20th of a pixel, again, including both plate solution and centroiding. 95th percentile is up at about a little over 2 arcseconds for the bright objects. And so that's, again, a 10th of a pixel. So we're doing really well. Also noting that there is no dependence on field. So the plate solution is good all the way out to the corners. And so the corners of the TESS field include 47 pixels of optical distortion. And again, we're able to correct for both the distortion and the plate modeling to, 75th percentile here in under 3 arcseconds all the way out to the corners. And this is for all magnitudes together in here. This data is from a set of 857,000 asteroid observations, for which the Minor Planet Center provided the truth data with the predicted position of the known object. So we're doing really well for bright objects and, as well as we can for the faint ones. So what are we finding? So these are all the asteroids we're finding, all observations of all asteroids at every point in time, including known and potential new discoveries. So this is a plot of the spatial density of the asteroid observations. It was really interesting hearing Christina's talk about tools for moving stray light. I want to look back into that. As you can see here, there's some regions we have a higher density of asteroid observations than others. We've tracked these to correlating with times of higher stray light. We can't go quite as faint. But when we have dark skies, we are able to push to really faint detections. And so we're getting a lot of interesting data out. One thing also to note, though, as excited as we are about finding asteroids, because this is the solar system science panel, so this is what we're looking for. If your goal is stellar light curves, you better watch out, because yes, there are a lot of asteroids there, and particularly when we're looking near the ecliptic. So I have here some examples that I pulled based on our work in identifying the locations of the asteroids. I cross-matched with the locations of TESS target stars and found plenty of examples where you have asteroid interference in your light curve. So if you have an asteroid crossing near a target star, if it's in the aperture of the target star, you'll get a momentary increase in brightness. It will look like a flare or some other event. But if you get an asteroid passing through the background pixels of your target star, it will momentarily over-subtract the background, and you'll get an event that looks more like a transit. And you can have multiple different events happening within a single sector. So it's just of note to make sure when you're doing validation on your transits, watch out for the asteroids. We can help provide information on where are all of the asteroids at all points in time based on our observations and on the catalog of known objects. So that is future work for us. And for lots and lots of details, here's the reference for our recent publication.
Thank you very much, Deb. So we got a few questions in the Slack channel, so I think we have time to discuss these. So one of the questions is, as always, I would say, is that what is the limiting magnitude of these processes? So Michael asked it, and he asked it whether it's in the range of 21, 22. So I think this is something that we can agree that Matt and Christina also mentioned this number. But if you have any thoughts that what can be said about this issue. And the other thing is which came up into the chat just related to this question, that what is the precision for the brighter asteroids? So does anyone have some sort of assumption that if we have a bright one, something like a 15 magnitude or even brighter, 12, 10, something like that, what is the per cadence precision? How does it relate to the precision of stars with the same magnitude range?
Astrometric or photometric precision?
Photometric, yeah. Photometric, sorry.
So I think, Christina, do you want to talk a little bit more about the 22nd magnitude number that you were talking about? Because that sounds like you've probably done more detailed and recent work than me.
Yeah. I would say this is currently anecdotal, and I do not have a figure to back this up. I think that over a week, we can probably get to sort of tens of % precision at 22nd magnitude. And that's like the limit, really, that we can pull out anything useful in terms of rotation rates. I don't think that our work is going to be able to go much fainter than that and produce extremely useful data products for people to use. If you've got more than a week, then maybe you could push it slightly. But yeah, I don't think that we can go fainter than 22nd and pull out useful information. What about you, Matt?
Yeah, so because I haven't really been sort of considering things in terms of like trying to get any rotation curve type things, so I've sort of purely been focused on saying what's the best I can get to by summing over an entire sector's worth of data. Then what I was sort of getting down to is sort of like for some average-ish sectors with in terms of like the background contamination, we were thinking that we can get down to around about 22nd. We can clearly pull out examples where it's like 21.6, 21.8, that kind of thing. So we clearly see those in, but some of those are in like fairly like good low background-ish areas of the sky. So then the worry that we've been having is about the worst areas of the sky with the sort of the bad background areas. But then your talk gives me some more hope about that with the tools that you're developing for the background subtraction to allow us to do that probably a bit more cleanly, or at least more smoothly than we've been doing so far.
Okay, so another question. Oh, there are many new questions, and one of the most interesting questions is that what kind of synergies can be between planetary and exoplanetary science? So what are the panel's most promising or underlooked aspects of planetary science that we can incorporate into exoplanetary science? We means the exoplanetary science community, not the solar system science community. So if you have any thoughts about that, what can be interesting for the exoplanet teams, exoplanetary scientists? And the other thing is the other question, which is just a simple question, that what about comets?
Yeah, so so I very sort of briefly alluded to sort of trying to detect interstellar comets, and solar system comets effectively found, from my point of view, sort of fall into the same sort of idea. You're trying to detect rare objects that are in a solar system, in and around this the main belt asteroid sort of region, perhaps a little further out. And many of these comets, both solar system and interstellar, are easily going to be at 17th, 18th magnitude. So almost going to be detectable straight away a lot of the time, directly in a single TESS exposure. So maybe for some of them, if you want to discover them a little further out, you need to do some small amount of shifting and stacking to be able to detect them, but the amount is minimal. So you can very easily get effectively an all sky survey for comets that will go down to 18th magnitude with like very little effort. So I think that's a great idea. And then for things like interstellar comets, it becomes a tiny little bit more difficult because you've got weird rates of motion due to the non-bound orbits, but it's not conceptually much more difficult.
Okay. I'm just trying to pick up interesting questions. Yeah, it's for Deb, that you mentioned that some of the signals which is caused by nearby asteroids could mimic the transits. And if you just look into details, does it really resembles to transit-like curves? So the shape will depend on the details, which pixels that asteroid passes through the background aperture. So is it a real issue? Or...
I think they can be distinguished based on this shape. I haven't looked at every case to see if there's any that can kind of fool you, but the timescales can be similar. The main belt asteroids are moving at 0.3 degrees per day. It's a few hours to transit across the background aperture of a star.
Okay.
So fast-moving objects, though, will have even shorter crossing times. So the background aperture, it's not a solid block, right? I'm sure you've seen the cutouts. They're like sort of pixelated. I think some pixels are not included based on if it's a crowded field or other conditions. And so I think it's going to be different case by case. But in general, I think the shapes should be different enough. But again, I haven't looked at enough cases to really say whether there's any potential asteroids causing that confusion.
Okay, and just I also mentioned in the introduction that in the primary mission and in the third year, the TESS avoided the ecliptic plane, but it's not true starting from the Friday following next week. So just starting from 2 weeks from now, when TESS try to observe the ecliptic plane until the end of this year, so for 5 sectors. And related to this, Malena asked that what can we learn if these nearby fields stitched together from different cameras and CCDs, which are moving from the CCD frame to the next one. So this is something related to the future. And she also asked that can bright asteroids with well-known properties be used as a kind of control sample to better characterize the TESS systematic errors? So it's related mostly to the photometry, what we do with TESS in order to get nice light curve rotation, stuff like that. So we also get this question. So if any of you has some ideas about this, so what can we expect starting from the next, not the next, next Friday following after the following week, and can this be used as a kind of brighter asteroids can be used as a kind of test case to validate the pipelines?
Bright asteroids, I think, were used in some space missions as calibrators, like in the Herschel mission. So maybe I don't know. I don't know by heart that is there a difference between the or a large difference between the different CCDs or cameras. So if you mean that getting some technical characteristics of these of the cameras, maybe we can get some information. In our case, we got the well, absolute magnitudes compared to the Gaia catalog. So there is a method to get these fluxes of these magnitudes, and maybe we can compare if there is a difference after a brighter asteroid goes to another camera. But I don't know yet. We will see, I think, or we can try. We will see, as we said, tens of thousands of asteroids in these ecliptic fields. So I think we will plenty of targets to test these.
Okay, so I think time is almost up for the panel discussion. So I would advise to everyone to just feel free to send the questions or any thoughts to the Slack channel, and then we can just start with Csaba, his presentation, and then we just continue with the Slack discussion later on, and of course related to the following two presentations, which will switch to from the inner solar system, except for Matt's presentation, to the outer regions of the solar system. So of course, just feel free to ask the questions on the Slack channel. So Csaba, please.
Yeah, can you hear me?
Yes.
Okay, so I will try to share my screen then. Just a second. So, can you see that?
Yes, but it's not full screen, not in presenter.
Okay, so this way.
Okay, that's good. Okay.
Good. So, thank you. So, my name is Csaba Kiss, and I'm from Congolese Observatory. And here is the team working on the light curves of dwarf planets with TESS. And so what can TESS do with Trans-Neptunian objects? Yes, as we heard it in the panel discussion before, it's either detection or light curves. So the light curves of small bodies are caused by rotation. The periods are typically from a few hours to several hundred hours. And of course, these light curves can be observed with TESS if the target is long enough in the field of view. But TNOs, Trans-Neptunian objects, are typically slow. So it's usually the case that they are in the same sector for 28 days or so. So we had a very successful similar program on the light curves of many dynamical groups and populations using K2 data. So if you are interested, you can just follow this link here. And as it was discussed, yes, there are lots of solar system targets, even several degrees above the ecliptic, and this is especially true for the Trans-Neptunian populations. And Trans-Neptunian objects are typically too faint for TESS, at least light curve wise, but good quality light curves can be obtained for the brightest and the largest ones, the dwarf planets. My estimate was here is something like 19th magnitude, but as we heard, it's probably, we can go somewhat deeper. But you need to have a rather bright object in this sense to have to be able to obtain low amplitude light curve. But for these objects, is it still interesting after 25 years of TNO science? Oops. Yes. So actually, the number of well-established dwarf planet rotation periods is surprisingly low in the among the Trans-Neptunian objects. It's roughly 1. This is the Pluto-Charon system, which is a double synchronized system. So, I mean, light curves of Trans-Neptunian objects is basically rotation. So why does rotation matter the rotation is probably not caused by elongated shape for these large objects. These are simply too massive not to be round, but by surface features. So you can kind of map the surface for brighter and darker areas. And if you combine the rotation information with satellites, which is where most of the dwarf planets have moons, so what you can obtain is like the angular momentum of the system, tidal evolution and formation, and information on collisions and the state of the planetesimal disk in the early solar system, and constraints on the internal structure and materials. And this can be done with a better determination of size and shape with combination of thermal emission data. And the three objects that we looked at so far are Aries, Makemake, and Orcus. And I'm starting with Orcus. And basically, this is an example. Well, you can just see how TESS observed Orcus in sector 9. And that's basically the light curve what we obtained with two characteristic frequencies which are very close to each other, probably due to these two sections in the data that we have. One is around 7 hours and the other is around 14 hours. And we think that the rotation is not fast enough to cause ellipsoidal distortion, even if the rotation period is around 14 hours. What we can do from this information, either with the 14-hour or the 7-hour, that we can calculate the expected flattening of these objects. And well, there is some model that can do that, and then it's roughly in the range of 0.1 to 0.15, depending on the mass and size. And we also know from other measurements where the satellite of this dwarf planet is, and what the expected aspect angle of the satellite orbit is at the time of the TESS observations. And so what you can do is you can model the observed light curve, assuming a double peak light curve. This is in the upper row here. In the double peak case, it would be an elongated ellipsoid, but it would simply require an extremely elongated body to reproduce the light curve. So the single peak light curve due to an albedo spot seems to be more feasible. And these four plots here are with different setups, but it's basically we can model the surface of Orcus assuming this dark spot. And you can also combine this information with thermal emission data, and from the thermal emission data, what you can most importantly obtain is the size of Orcus, and the size of Orcus now is constrained to something like 840 kilometers. And if you calculate from this the density of Orcus, the mass is known from the binary orbit, then it's just 1.855 grams per cubic centimeter, which is exactly the same as Pluto, which is interesting in itself. But what is very interesting in the case of Orcus is that if it has this 7-hour rotation, then this is a very fast rotator. And as the moon is seems to be rather massive, it should have slowed down the rotation of Orcus. So we put this into a simple tidal evolution model. I'm not going into details. The main conclusion here is that yes, it's possible that there were setups at the formation and impact formation of the Orcus 1 system, but that requires that the moon should have a relatively low density, otherwise the system would have reached spin lock state. If the wound-forming impact occurred 4.5 billion years ago, there's of course the escape route that the impact was just a recent one, but it's very unlikely concerning the current or not so late density of objects in the Kuiper belt. So we can do the same basically with ARIES. This is the ARIES light curve with TESS, again with two possible frequencies which are much slower. So this object is almost slowed down to, well, not exactly slowed down to synchronous rotation, but it's a very slow rotator now. But with a much smaller primary to secondary mass ratio. So then we have the question that how is it possible? We just, before going to the final slide, just have a look at the third object, Make Make. It's also here the rotation period is something like 8 hours, which is good. It's not extremely fast. It's not extremely slow, and the moon is small, so it's likely kept its original rotation period. So my final slide is a kind of summary of a few objects, the largest dwarf planets and their satellites. Here the mass ratio of the primary to secondary, no, the secondary to primary is plotted versus the angular momentum of the system compared with the angular momentum of a body containing the total system mass and rotating at the mass ejection limit. So there are some numerical simulations with the result that the satellites formed in a single large collision should have this J over J prime ratio around 0.4. It's like in the case of Pluto and Charon. And as you can see, there are many possibilities here where these systems could be. For Orcus 1 is a high Q, high J over G prime, fast spinning object. Pluto, Charon is a high Q, high J over G prime, double synchronous system. Aries dysnomia is a medium Q, low J over G prime, slow rotation, but not synchronized system. So the final question is what makes these systems formation and tidal evolution wise so different? And the light curves from TESS is a very good tool to try to answer these questions. And that's it. Thank you.
Thank you very much, Csaba. You got one question.
Yeah.
What's with Homer?
Just what's with Homer? That's in general. I mean, Homer is very fast spinning.
I mean,
so,
what's with Homer rotation light curve? I suppose Elizabeth was thinking about TESS.
Yeah, that I don't know. That probably you know whether it's going to be observed. But I think that I know. Yes, that's the other one which is very well determined. Yes, that's right.
Okay.
I was wrong. I was wrong with the number of 1. It's
so that's
2.
2.
That's 2. Yeah, sure.
Okay. Thank you. I think we can just proceed with the last presentation, from Malena Rice. And then we're just waiting for other questions in the Slack channel.
All right.
Csaba, can you stop the screen sharing?
I'm trying to, but I cannot see the. Or you just can kick me out as presenter.
I think I can override it.
Maybe you can, yeah. Thanks.
All right.
Okay. So we see you, Malena. So I think you can just perfect. Okay, now it's full screen.
Yep. All right, so I'd like to thank the organizers for the opportunity to be here and to speak to you all today. And thank you all for tuning in. My name is Malena Rice, and I'm a rising 5th year finishing PhD student in the Yale Astronomy Department, working on the dynamics of planetary systems. And I've been hard at work wrapping up a few different dissertation projects over the past few months. And today I'm really excited to share with you an overview of one of my more extended efforts to lead an all-sky shift stacking survey of the distant solar system with TESS. So the goal of this survey is to stack TESS full-frame images to find undiscovered slow-moving Trans-Neptunian objects. And I'll start off by describing some completed work that was published late last year, and then I'll go on to describe some of my ongoing efforts. Okay. So if you watched the panel or Matt Payne's introductory talk, you might be familiar with this plot that shows the parameter space that is spanned by known objects in the Trans-Neptunian solar system. The minor planet populations shown here really lay our foundation for our understanding of the solar system's early dynamical evolution. So they're a really compelling group of objects to study in detail if we want a deep understanding of how planetary systems form more generally. In my talk, I'll focus primarily on the detached Kuiper Belt objects and why that particular population. Well, Shepard and Trujillo 2014 found that the periastra of the long-term stable detached Kuiper Belt objects appeared to be clustered in one particular direction on the sky. And that's these purple orbits that you can see that are sort of all angled downwards here. And that's not expected because the orbits of these objects should precess over time at different rates such that they would spread out across the sky over a span of about 1 billion years. So the solar system is not a two-body problem. We don't have a perfectly Keplerian potential. And because of that, we get orbital precession that ends up spreading out these orbits at slightly different rates so that they shouldn't all just be clustered on one side of the sky. Similarly, Batygin and Brown 2016 found that the longitude of the ascending node, which tells you the relative planes in which all the orbits lie, was also unexpectedly clustered. So if this is real, and if it's not an observational bias, then it might suggest the existence of an as yet undiscovered planet that exists in the distant solar system that is commonly known as Planet 9. So if Planet 9 exists, it's predicted to be a sub-Neptune planet on a moderately eccentric and inclined orbit located hundreds of AU from the sun. And these detached Kuiper Belt objects that I mentioned earlier, they've been found by a lot of different surveys. So each survey finds a couple of them, and then they're all combined to conduct some sort of statistical analysis and determine whether this apsidal alignment appears to be real or not. Well, one of the limitations of that is you have all these different surveys, they all have different systematics, their own idiosyncrasies, and something really powerful about TESS is that it's observing the entire sky as a uniform survey. You're able to place detection limits with just one telescope and just one survey to determine, first of all, whether that apsidal alignment appears to be real, put some constraints on whether this is an observational bias or not, and then also to potentially look for this planet itself. So those are sort of the two primary goals of this survey. Okay, so let's dig into how we actually search for these objects using TESS. In all of the primary mission and all the extended mission data so far, the TESS cameras have been aligned parallel to the ecliptic plane as shown here. And this is really convenient because distant solar system objects are effectively static in their orbits relative to the Earth. So really what we're seeing is actually just Earth moving past, and Earth moves in the ecliptic plane. So we're just seeing the parallactic motion of the Earth moving past these effectively static objects that are just on such large orbits that they're not really moving very much, and they effectively move left to right within the TESS frame. So that makes it a lot easier. We don't have to search every single possible direction to look for these objects. The range of paths is relatively limited. And to search for the objects, we're going to have to do a little bit of pre-processing. We're looking for really distant objects, so they tend to be below the single frame detection limit, and you're going to need to stack a lot of images to actually pull them out. So we developed a shift stacking pipeline that is designed to process these TESS full frame images and search for the signals of very dim outer solar system objects that are below that single frame detection limit. We first mask out really bright pixels, cut away frames with complicated systematics, then we fit the remaining time series pixel by pixel. So every pixel gets its own fit that's then subtracted away because we're just looking for deviations along some path above the baseline flux. So we want to look for tiny deviations along a path that we then add up to get our final signal. And then when we shift and stack the frames along all these paths, then we're looking for local maxima that correspond to perhaps some real signal that we're interested in. And I'll note that we do this with two different methods. So I'll walk you through the polynomial fitting method, which is kind of straightforward. You fit polynomials to each of the pixels. We also use principal component analysis with the light curve Python package. And we use both of these to validate each other and to have two different methods to identify each of these potential candidates and then to see if they show up in both of them. And so if they show up in both of them, then we believe the candidate more than if it just showed up in one reduction method. Okay, so more concretely, this is just two different frames that contain the extreme trans-Neptunian object Sedna, which is a very distant object. It has V equals about 20.6, and it's located in the pixel with a black dot in the image to the left and in the pixel with the red dot in the image to the right. So you can't really see any obvious change in flux as it's moving through, because there are a lot of stars and other things in the frame that are contaminating the image. So in our pipeline, we take the entire time series, we mask out the data downlinks at the beginning, middle, and end of the sector, and then we end up with a curve that looks like this. In the polynomial method, we just fit polynomials to those two sides, subtract them away, and we do that for every single pixel in the image. So our initial image ends up looking sort of just like noise by the end of this process, which is exactly what we want. We want some pixels that are positive and negative, and we're just looking for deviations above that baseline along some path. So if we're looking for an object that moves across the image in some way like this, so it's going to move, again, mostly from left to right, then we could equivalently just follow the object and instead move the image past. So this is kind of an example of that. And that's the idea behind our shift stacking process. So this is a video from my paper that was published that is demonstrating a little bit more concretely with TESS data what exactly this ends up looking like. So after subtracting the baseline flux from every pixel, we slide the images past corresponding to some orbit of interest, so some particular path, and then we stack up all of the images to actually pull out the particular object that we're interested in. So in the left panel here, you'll see our baseline subtracted frames over time. This is basically a video of the sky where we've masked out the bright stars that are in the frame, and we're just seeing asteroids moving through. On the right side, we start out with this big blank region to the left side of the frame that gets filled in over time as we're shifting and stacking the frames towards the left. And so then we get Sedna that pops up in this nice central region. And that's how we're able to pull out these really, really dim objects at really quite high signal to noise. So it pops out as kind of the only really, really bright point source that you see in this object or in this image. We demonstrated, so that was kind of demonstrating how we can find a known object, but then in order to find undiscovered objects, we need to conduct this process many times along many different paths. And so we create something that I call a best ever frame. That's an aggregate frame where we check all of these possible shift stacking paths. And for each pixel, we just retain the highest flux that we got along every single path that we check. And something that is helpful about using this method is we're able to just look at a smaller number of frames. There's a huge data set of just test data to look at. And so by looking at a smaller number of frames, it makes it a little bit more tractable to search the entire data set. And it also allows us to directly compare the results that we get in a given region of space. So we can see, does this particular point source look more compelling than anything else in that particular region of space? And that helps us to gain confidence in any particular detections that we might get. So these are just 3 example objects that we ran this method on. Sedna, BP519, and TG422 are the 3 rows, and these are sequentially dimmer objects. And then in the left panel, this is just a shift stack where we know exactly where the object is. We shift and add together the images along that known path. But then in the middle 2 columns here, these recoveries incorporate no prior knowledge of the object's orbits. Here, these are those best ever frames where we're just checking every linear path. So we're assuming that it's a linear path because we're assuming the Earth's parallactic motion dominates for these really, really distant objects. And we just search all the linear paths that correspond to orbits between 35 and 800 AU. And Sedna and BP519 pop out really nicely. TG422 we don't recover, probably for 2 reasons. The first is that this is the dimmest of the 3 objects, so it's going to be the trickiest by default. And then it's also the most nearby of these 3 objects. So this is kind of a good example of where you start needing to actually consider nonlinear paths when you get closer in the solar system. So TG422 is at a distance of about 37 AU. It's closer than these other objects that are 55 AU-ish and farther. And because of that, we start needing to actually think about nonlinear shift stacking, which I'll talk about a little bit at the end. But for most of our objects, we're really looking much farther, especially if you're looking specifically for Planet 9, you really don't need to take into account nonlinear shift stacking for that particular purpose. But there's another caveat here, which is that all 3 of those objects were located in Sector 5, which is this relatively nice, clean region of the sky, but not all of the sky is going to look like that. And specifically, we have the galactic plane that's slicing through a lot of these test sectors. It is the region of the sky that has the most stars in it, and that is going to make it pretty difficult to pull out these really, really dim objects, just because there's a lot more background noise in these regions of the sky. So to address this, we also characterize the recoverability of dim distant solar system objects in those particular regions of space using injection recovery tests. So we picked 2 sectors that go directly through the galactic plane and just characterize how well can we actually pull out very dim objects in these sectors. I'm not going to have time to go through all the details here, but the main takeaway is that our survey was complete for objects out to about 21st magnitude and 150 AU, and our PCA baseline subtraction method typically performs better than our polynomial method just because we get less self-subtraction. And this initial paper was really meant as a proof of concept. So we've done further work to refine our pipeline. This is our initial published recovery of Sedna that you can see as this point in the middle. And once we mask out the foreground asteroids that were in that initial video, we can refine our return signal. And then with some more adjustments to the pipeline, being more careful with stellar masking, maximizing the number of data frames that we preserve in our recovery, then we're able to extract this signal that's a lot cleaner. So we've been putting a lot of time and care into improving our reduction methods so we can make the most of the existing data set before we extend to an all-sky survey. And really the goal is to carry out this all-sky survey with the help of neural networks, which streamline our candidate identification process and also help us to concretely characterize our false positive rate, which is really important. We don't have a good constraint on that just yet, and that's something that these neural networks will be really helpful for. This will also tell us what region of parameter space we're really sensitive to, where the nonlinear shift stacking is necessary, where the linear assumption breaks down. So we have 3 different layers of information in our networks where we have the injection as well as the X and Y shifts that correspond to the signals that we've injected. So we're using these best ever aggregate frames as inputs to the neural networks. And these are just some examples of some diagnostics that we have. This isn't our final model. We're still working on kind of characterizing what the best properties are in order to actually get the best possible results from our model. But this is just an example of the type of behavior that we're getting right now and sort of our expected results that we anticipate we will be able to get. So hopefully we'll actually refine a little bit further beyond this, but that's just a sense of where we are at right now. And we're also thinking a little bit about nonlinear shift stacking. So this is something that is going to be necessary for more nearby objects, and you can actually create just a dictionary of the minimum number of paths that you need to check in order to consider all orbits in a particular parameter space of interest. So you can create a large library and narrow it down, TESS has relatively large pixels, so it actually wouldn't be that large a number of paths that you would need to search. It would be more of a computational problem, and we actually know exactly where TESS is. We can take into account the orbit and everything, so that can all be done very precisely. So it's something we've been thinking about a little bit, but haven't really needed to implement for this particular use case. So we haven't gone into too much detail, but it is something that we're considering. So I'll leave you with my conclusions, and I am looking forward to taking any questions. Thank you.
Thank you very much. So while we are waiting for the questions, still on the Stack channel for a minute or two, I have one question related to your plots of Sedna BP 519 and TG. That it's how does these detections depending on the color of the object? Because you just listed here V magnitudes, but TESS is observing in near infrared, so it's almost like an I band. And if if the objects are reddish, then it might make a difference, a quite significant difference in this very faint. And so did you make any check related to the colors in this aspect?
Yeah.
I'm not really sure that, sorry to interrupt, sorry, just another thought that it's, that probably there's no information available for these objects. But probably there is something, I don't know. That's why I'm asking.
Yeah, we do know the albedo of Sedna, at least. I think we do know the albedos of these objects. I'm not sure how well the colors are constrained. And I wonder if we might be able to actually get that a little bit better using TESS. So these it would probably be good to check what the I band is for. I think the first two were also in the Holman, Payne, and Paul and the Payne, Holman, Paul papers. So I think they actually did report I band there. But TG422, it would be good to actually check what that one is. Okay. I was just using V magnitude as like a diagnostic, but yeah.
Okay, so thank you. And you also got another question that just in very last minute, that do you expect to be able to detect Planet 9, definitely rule out potential orbits once you start your all-sky survey, or is it through to be too faint for TESS?
Most expected Planet 9s should be detectable. So Planet 9 should be around V is, and this is why I was using V magnitude, it should be around V is 19 to 22 or 23. And so TESS wouldn't be able to see it if it was around the very dimmest of that range, but it would be able to see it across most of the possible parameter space. And then if you start thinking about adding together the different returns to a particular part of space, then it might be more and more feasible. Yeah, but I think it will be able to narrow down at least a pretty substantial region of Planet 9 parameter space, but it's hard to actually rule out a planet by just saying you don't see it, because you never know if it's just really close to a very bright star or something like that.
Ah, okay. Okay. I think we are run out of time, but you also got another question in the Slack, so probably we can just jump on the Slack and then we can have a short break according to the schedule, and then I think Avi and Jen will announce the last panel, if I'm right.
Thank you, Andras.
Thank you again, everyone.
We will have a short break now until 10:30 Eastern Time, 2:30 p.m. UT, 4:30 p.m. Central European Time. While we are on a break, the panelists for the next panel can quickly check their connection, see that they can share their slides okay. If they have any videos they want to test, they can also do that now. Hello, Nicole.
Good morning, afternoon, evening.
Hi, Willy here. Can I make you try the sharing the screen if it works?
Go ahead, please.
Okay, thank you. Can you see my screen?
Yeah, looks good.
Okay, good. Thank you.
Do you have any movies that you want to
No
check?
movies, just slides,
Okay.
just a few slides. So it looks like it works.
Yes. Okay.
Thank you.
Anyone else want to do a quick check?
Will I go next?
Yeah.
Does that work?
Yeah, looks okay.
Great, thanks. Can I try?
Yeah.
Let's see if I can. Just allows me to do desktop, not the whole.
Yeah,
Does that
looks
work?
good. Yeah.
Okay. Perfect.
Giovanna, do you want to make a quick check?
Yes, thank you very much. I was exactly thinking of that.
Yeah, we can see the
movie. Yeah,
we can see the movie. Yeah.
that's perfect.
Right.
Thank you.
Okay, looks like we are all set. And Nicole, you can start in 5 minutes when we finish the break.
Okay, will do. Thanks, everybody. We'll get started in 30 seconds or so. Let folks log back in after the break. Okay, we'll go ahead and get started today. Welcome everybody to the final panel of TESS SciCon 2. I'm glad if you're here, you made it to the last day. It's Friday or maybe almost Saturday in some places. So in our final panel, we have the honor of hearing from 4 leaders in our field who all play key roles in some of the new and upcoming astrophysics missions. We, of course, do not have time to highlight all the upcoming exoplanet and astrophysics missions, but you know, we did our best and we have some great ones to hear about today. So our panelists today are include Willy Benz from the University of Bern, who will tell us about CHEOPS, Heike Rauer from the DLR Institute of Planetary Research, who will tell us about PLATO, Susan Mullally from the Space Telescope Science Institute, who will talk to us about synergies between TESS and the James Webb Space Telescope. And then finally, Giovanna Tinetti from the University College London, who will speak to us about ARIEL. So as a reminder, if you have not yet had a chance to view the longer recorded presentations on these missions from our panelists, those are available for you to view on YouTube. And today in this panel, following the other panels that we've had this week, each speaker will first provide highlights on the different missions, and then we will have a question and answer session at the end. So if you do have questions as we go along, of course, feel free to type them in the new missions Slack channel. That's new-missions. Okay, so to kick things off, I will hand it over to Willy Benz, who is professor of astrophysics at the University of Bern and the principal investigator of the CHEOPS mission. So Willy, take it away.
Yes, thank you. Let me start sharing my screen. Here we go. I hope everything works fine. So let me get things sorted out here. Well, first of all, thank you for having invited me to speak about CHEOPS in this panel on future mission. But I must say, I feel a bit odd speaking in this panel because CHEOPS is not really a future mission. CHEOPS is actually flying and delivering outstanding science since April last year. The good news is that the satellite is working as expected, if not better. And you probably had the opportunity to hear about some of the results during the session on Wednesday. If you haven't had the chance, the session, I believe, is now on the YouTube channel. In a nutshell, CHEOPS is the first small mission in ESA's science program. It carries a 30 centimeter clear aperture telescope designed to make high precision photometric measurements in the visible. CHEOPS orbits the Earth in a dawn-dusk sun-synchronous orbit at 700-kilometer altitude. CHEOPS is not a discovery mission such as TESS, but a follow-up mission, providing the means to go back to look at the most interesting objects already known and improve on or extend the measurements already made. Selected in 2012 by ESA and launched in December 2019, it has a nominal lifetime of 3.5 years. By construction, CHEOPS needs a detailed list of objects to follow. It needs to know where to look and when to look. It is therefore only limited by the ability of the discovery facilities to provide the targets to follow up. As target providers, we use objects from ground-based RV surveys or photometric surveys, as well as space-based facilities. Finally, since CHEOPS is only pointing at already well-known target, it does not have to deal with the usual issues related to false positive and so on. So it's easier. Photometric precision was the major driver in the design of the mission. It turns out that this has paid off, with actual measured precision exceeding requirements by a comfortable margin, as you can see on the left panel here. On the right panel, we show a comparison between TESS and CHEOPS light curves for the bright star Nu-2 Lupi. This illustrates a synergy resulting from the different approaches. Harvey survey discovered the 3 planets orbiting Nu-2 Lupi. TESS confirmed the inner 2 were actually transiting, and CHEOPS, by following up the system, not only discovered that the 3rd planet was transiting as well, but also improved on the radius measurements of all the planets. As multi-planet system offer strong constraints on planetary system formation, it is of the essence to have the best possible characterization of these systems. CHEOPS science is very diverse and reflects the scientific interest of the science team. As photometric follow-up mission, CHEOPS provides the intermediate step between discovery and the full spectroscopic characterization expected by JWST or ARIEL. You have here the list of published papers with the color indicating the scientific themes to which the paper is related. And I can only encourage you to go look at the full talk and the session on Wednesday. Finally, if you believe CHEOPS can be useful to you, you can actually use it through the ESA Guest Observing Program, which is open to everyone. You can find all the relevant detail on the website indicated here. And if you don't have time to copy it down, just Google CHEOPS ESA Guest Observer and you will find it easily. Thank you very much for your attention.
Excellent. Thank you, Willy. That was perfect timing. So next we'll move right on to Heike Rauer, who is head of the Institute of Planetary Research of the German Aerospace Center and the principal investigator of the PLATO mission. So take it away. And you're still muted.
I forgot. I have to unmute before I share the slide. After all this time, I still forget it.
No problem.
So I hope you hear me now and you can also see my slides.
Perfect.
So PLATO indeed is a future mission. And I'm speaking here on behalf, of course, of the whole PLATO consortium. So what is PLATO? I want to give you a short introduction in this. PLATO is an M-class mission of ESA, so it's a middle-class mission, a bit larger than in volume, financial volume than CHEOPS. We are now in the phase C. For those of you who know about project developments, that means we start to build breadboards and engineering models and test and even first flight models. Parts are becoming real. The launch of PLATO will be at the end of 2026. This is still our schedule. And we will go into an orbit of around the L2 Lagrangian point of the Earth sun line. So we will be going around the sun with the Earth and be in a position to point at almost our sky. If we wouldn't have the sun and moon and Earth stray light concerns, but I will come to that in a minute. So what is PLATO doing? It will provide high precision photometry of stars, target stars. Our main magnitude range is from 4 to 11th magnitude, but we can go down to 13th magnitude. But for all stars which are brighter than 11th magnitude, we get 50 ppn in 1 hour. And this means we can reach our precision goals that I will show you in a few minutes to characterize the radii and masses of our planets. Now, how do we do that? Here you see a picture how the PLATO satellite will look like. And it's very different to the usual expectation that you have from a telescope. It's not one big mirror. It's like it is divided into small cameras that in contrast to TESS, where we have the 4 cameras that look at different parts in the sky. Here in PLATO, We have 24 cameras, which are divided into 4 groups of 6, so each one of these. And they look at an overlapping field of view in the sky. So we have a field of view that looks like this. We have all 24 cameras looking at the same position in the sky in the center. And then because these groups are opened a little bit by an angle, 6 of these, we have 6 cameras observing the same field of the sky in the corners. The cameras are mounted fixed on an optical bench. So they provide a very large field of view of 2,100 square degrees. And to the right here, you see as an illustration, a comparison of the PLATO field of view. That's this blue flower-like field here in comparison to the Kepler field, the yellow field here at the right for comparison. So here to the left, you see some mass and thermal dummies of our buffers of the cameras coming actually from Bern, Willy. Just to give you an idea how these will look like. So 26 cameras, each 12 centimeter apertures, and then in addition 2 fast cameras, fast because they have a faster readout cadence of 2.5 seconds in comparison to 25 seconds that help to the pointing of the satellite and will observe the brightest stars. So now when the satellite is launched, we have 4 years of operations time as a baseline given by ESA. And so we have the trade-off to make between staring very long at one field, like Kepler did, or covering larger regions of the sky. And you have to think what to do. You have to make a decision what to do. And as a baseline, we decided to split the 4 years into observations of 2 times 2 years and observe 1 field in the north and 1 field in the south. Now, don't read the exact coordinates of these blue regions here from the plot. The exact pointing is not finally fixed yet. It will be fixed 2 years before launch, but these are about the regions in galactic coordinates here where we will point. So 1 northern field, 1 southern field, but we can change the observing mode if we like. We can decide to stay for 4 years on 1 field. And of course, we hope for mission extensions. The satellite will have consumables for 8.5 years, so we can in principle observe up to 8 years with this mission. We just have to ask for mission extension. So now, what are the methods? Like TESS, what the satellite provides is light curves, high precision photometric light curves, and in these light curves, we will search for transit events. So it's a real detection mission like TESS. The transit events, as you all know, provide the radius, period, and inclination. And we will complement this by an intensive astroseismology program for stars to provide the stellar parameters and the ages of the systems. Together with a ground-based program, and this is a difference to TESS. In case of PLATO, the consortium is responsible for organizing this ground-based program. And that means we are organizing a big community effort. And if you want to be part of it, let us know to get the needed radial velocity data to get the planetary masses. So our goal with the satellite is to provide radius with 3% precisions, mass to 10% precision, and the same 10% for the ages. And this is for a benchmark case, which is the Earth around the Sun. So it's the most difficult case if you think about measurement, because the Earth is very small. But of course, it's also the most interesting case. So we take that as our benchmark for the engineers to design and build the mission. So this is our goal. And once we have these, what do we want to do? Well, what we can do, of course, in not only detect planets, but also because we will have a good age of planetary systems, we can compare planets and planetary systems at different ages and see together, and this is something maybe we can discuss in the panel when we can put James Webb observation, ARIEL observation, PLATO, and CHEOPS all together, be able to study evolutions in typical classes of planets. That's at least dear to my heart, and that's what I hope that we get out. So from a statistical point of view, one point, of course, is the eta Earth, how many stars have small planets. There, Kepler, K2 have done a great job, but this is just from a paper where these Kepler data have been reanalyzed, and we see that The Earth around the sun case is still difficult. We don't really have occurrence rates for small planets, and we don't have radii masses and ages to very high precision. And here I encourage you to listen to the session and the panel talk with Diana Valencia, where she clearly assessed that for the terrestrial planets, the rocky planets, where the atmosphere part is small, radius masses can give some clue on the interior, and that's why we want to have these very high precisions. Okay. So what is the comparison to TESS, or the complementarity to TESS? How does this all fit together? Here we should have a plot where we have the stellar masses versus the semi-major axis, and all dots are small planets. Small means less than 10 Earth masses. And here we have the solar system, Mercury, Venus, and Earth. The green area is the habitable zone. And we see the habitable zone moving closer to the star for the cool M-dwarf stars. Here's the TRAPPIST system, for example. And the parameter range of K2, TESS, and ground-based is mainly here in the short period planets tackling the M-dwarf stars up to the K stars, or cool K stars. And what is left is the solar system analogs, and that's what we want to do with PLATO. And this is just the illustration we use to visualize what we want to do. We want to get the precise radii and masses, as I said already, good ages, and this will help us to understand how planets form and evolve. Put the solar system into context by addressing this still empty parameter space, and tell us a lot more about rocky planets and potentially rocky habitable planets, because many of the rocky planets that we study now are close in, they are hot, and we need to compare these to temperate planets out here. Another complementary I see to TESS is, of course, for the TESS detections that are made here, which are exciting. PLATO will be able to detect planets that are further out, beyond the habitable zone. And we don't really know what to expect here. This is interesting because we don't have such planets yet. So altogether, I think we are entering a decade of exoplanet and stellar characterization. And the piece in the puzzle that PLATO will add is mass, radius, mean density, and ages with good accuracy, in particular for terrestrial planets and sun or sun analogs. And there's a lot of synergy with TESS. Not only the refined planetary radii improve stellar ages, but of course we will extend observing baselines, since TESS covers the whole sky. For sure there will be TESS targets also in the PLATO fields. And for these, we will have a huge baseline of observations. And then, of course, the bright targets from PLATO will also be targets for the James Webb telescopes, which we hope will still be operational then, and ARIEL and ground-based the same, to bring the characterization further by studying the atmospheres in chemistry. So with this, I think I want to finish. There are a lot of science cases that can be addressed when we have all missions and we can put everything together. So thank you very much. And I'll pass to James Webb.
Thank you so much. Yes, perfect. So that's right. Now we'll hear from Susan Mullally, who is the Deputy Project Scientist for the James Webb Space Telescope at the Space Telescope Science Institute. And also she was previously the lead archive scientist for TESS at the Mikulski Archive for Space Telescopes. So take it away, Susan. And you're muted as well.
There's too many buttons to push before you start talking. Hi, everyone. Great. Thank you for inviting me to tell you a little bit more about the James Webb Space Telescope. It's great to be back with everybody who works on the TESS mission. It's been good seeing old friends in the Gather Town. So thanks you for the organizers for putting together such a great meeting. So I put together this talk with kind of the goals of trying to figure out the scientific overlap between what a 10-centimeter photometric survey is and what a 6.5 meter mid to near infrared spectroscopic and imaging telescope have. And it turns out there's a lot, and you can't possibly fit that all into 20 minutes. So I did my best to highlight some of the science that would be of most interest to this community. And so And then I also had the second goal of hoping to encourage you to be inspired to use the James Webb Space Telescope in the future. Webb is going to launch at the end of this year. And so I'm hoping that all of you are thinking about the best way we can make use of this resource. Okay, let's see. Clicking advances my slides. So as a quick overview, Webb is a 6.5 meter diameter mirror. We're sending it out to L2, which allows it to get cool enough to observe in the near and the mid infrared. It will last for at least 5, hopefully 10 years in its mission. It has 4 instruments on board that cover a wide variety of different observing modes of imaging and spectroscopic imaging to just spectroscopy, and many of these are time series observation modes, which I think would be of key interest to this community. The other thing to really realize is that 90% of the observing time on Webb is completely open for people to put in proposals, so that to choose from an open call. So we need you to put in proposals to figure out what to do to observe with this telescope. And I hope to encourage you to do so. Just this last year, we had the first call for proposals for the general observers, and we have now approved more than 10,000 hours of observing time for the first cycle. As a result, it's going to last more than 1 year, close to about a year and a half to get all those observations done. And it includes about 6,000 hours from that general observing time. And I've just quickly showing on this plot how that was split up amongst different science cases. And you can see that exoplanets and disks and stellar physics and solar system, many of the topics that we've been talking about here at this conference make up 30 to 50% of the observing time on Webb. And so now what I'm going to do is highlight some of those specific science cases that have kind of in a general terms. But if you want to know more about how people are actually using this telescope, I highly encourage you to go to the science execution page of the jwst.stsci.edu webpage, because under there you can find all the approved programs and the actual abstracts and what has been approved to do with the Webb telescope. So I'm going to move forward without mentioning specific programs and names, not that they don't deserve absolute credit for all of this, but it just became too much and slides became too crazy. So go there to find out these very deserving PIs for their proposals. So some of the science cases that I would like to highlight. First, I completely forgot about solar system when I put in my talk, so I had to add one in here. Webb absolutely is observing many of the objects in the solar system, pretty much everything from Mars outward, because we can't point towards the sun. Some of the things that overlap with the session that I was watching this morning, that Webb is going to be your way of following up interesting targets, for instance, amongst the asteroid population. There's proposals to do the volatile content of these asteroids. There are proposals to look out at Trans-Neptunian objects to characterize them, and also some to look at some of the dimmest ones, some of the smallest ones, which will help hopefully give us a sense of the smaller end of the TNOs, unlike the more brighter ones that I was hearing about that TESS will find. Amongst stellar physics, well, was way more in stellar physics than I could possibly mention. So a few thoughts on this. First of all, TESS just serendipitously will monitor the photometric standards that Webb is using. And it has already done it for about 36 or so of the candidate photometric standards, and it will tell us whether or not they are variable and help us select what the best photometric standards are. There's a poster here by Michael Kuntz if you want to know more about that. Amongst more science cases, Webb is going to do a lot with brown dwarfs, for instance. It will characterize their atmospheres, look for clouds, study their multiplicity, and search for brown dwarfs and young clusters, for instance. There's also on the other end, massive stars that go supernova or kilonova. And because Webb has target of opportunity abilities, you can put in to observe supernova right after they've exploded. or observe some of the more, they're also observing some of the more evolved system with the imaging and spectroscopic capabilities of Webb in order to better understand the physics and how these events influence the chemistry of our galaxy. And then, of course, there's huge overlap in between Webb and TESS, and that TESS has done a spectacular job of finding some of the planets orbiting nearby bright stars. And you can see in this figure of planet radius versus equilibrium temperature of the transiting exoplanets that Webb is going to observe. And then I've highlighted with white boxes the TESS discoveries, and I believe this is only about 90% complete. But you get the point in that the reason we have so many planets in that sub-Neptune region is because of TESS, that they were able to discover loads of planets that we can now characterize the atmospheres of those planets. And as a result, we're going to be able to explore the diversity of exoplanet atmospheres across a ranges of sizes and temperatures and ages and stellar environment. And also be able to look more in depth at some of these smaller planets and determine whether or not there's atmospheres on them. And if there are, we can determine their basic composition and look for things like carbon dioxide and methane. It also has allowed us to look at more diverse planets, like the planet that was talked about on Wednesday, about the planet orbiting white dwarfs that was discovered by TESS. And as a result, be able to look at the first cool giant with transmission spectroscopy. Using many of so a lot of these are using many of those time series observing modes that are available with TESS to do both transmission and eclipse spectroscopy. And so I'm just going to leave you with a few thoughts that if you haven't started thinking about putting a proposal in for JWST, you might want to do that, start thinking about that now. Here's a few thoughts and ways to do that. First of all, get familiar with JDocs. It is actually amazingly complete and completely searchable by Google, actually, so completely indexed by Google, so you can get in through there if you would like. And it will be updated soon, including improvements in how to do time series observations. But also keep in mind that after commissioning, which happens about 6 months after launch, that there'll be a lot of information that will be updated in there as we begin to understand our instruments better. Something you can also do now is start to familiarize yourself with the Webb data. There is already loads of examples of simulated data that you can get from jwst.stsci.edu. You can also work with that data in a class called the JWebinars. These are a virtual series of classes that you can attend that show you some of the tools in Python that you can use to work with these data and visualize them. And of course, some of the first data that are going to be available for everybody to see are the early release science program data. So take a look at those programs and find ones that are of interest to you. And you can then know that that data will be taken in the first 5 months and has no proprietary period. And so you can also get involved with those teams. A lot of them are open, or at least find out what they are hoping to provide for the community with those data as well. And as always, if you have questions, ask the help desk. They're extremely helpful. So thank you for giving me this opportunity to talk about JWST.
Thank you, Susan. All right, and then we have one more panelist, Giovanna Tinetti, who is head of the astrophysics group at the University College London and the director of the UCL Center for Space Exochemistry Data and the principal investigator of the ARIEL mission. Take it away. And you are still muted. There you go.
Exactly. Thank you so much, Nicole. Thank you so much for giving me the opportunity to say a few words about ARIEL. So ARIEL has been adopted at the ESA M4 mission in November 2020. We are talking about a mission that will be launched in 2029 in L2. And is composed of a 1 meter class telescope. And the idea is to do simultaneous coverage in terms of spectroscopy between 0.5 down to 7.8 micron in the infrared. So the entire idea of ARIEL is to monitor about 1,000 exoplanet atmospheres. And so bringing in basically the larger statistics The payload consortium that will build the instruments of ARIEL is composed of 16 ESA countries. We have a participation from NASA through the CASE team, but there will probably be a NASA call later on for a stronger scientific participation to ARIEL, and potential participation from JWST and Canada are under discussion. The idea of ARIEL is to have this survey of exoplanet atmospheres that are including very diverse type of planets, very different temperature, from very hot planets down to relatively temperate, in particular if you're considering the giant planets around all sorts of stars, and really try to understand what is the chemical diversity of all this atmosphere, what is the structure of all these atmospheres. And certainly when it comes to the giant planets, we can push the observation to extract even elemental composition. And the idea is then to use all this information to understand much better how planets are forming and evolving in our galaxy, using their chemistry basically as a tracer of their history. So given that we want to be very efficient in terms of breadth, but also depth in looking at individual planets, but also population analysis of planets, what we thought of doing was a sort of a 4-tier approach where we start with a survey at the relatively low resolution of 1,000 planets, and then we select out of those half of them for full spectroscopic characterization. And is this tier 2 sort of deep survey that will be used really to measure very accurately the composition of the atmosphere, the trace gases, thermal structure, clouds, and of course for the giant planets, really pushing for the elemental composition. We want to understand also the atmospheric circulation of these planets, and so for a subset of planets, we will keep monitoring them through time to try to understand spatial but also temporal variability. And we certainly also want to, for a subset, observe this planet through phase curves, and so doing a much more in-depth type of observations. Given that this conference, of course, is focused on TESS, and TESS, of course, is extremely important for us. We are based on this 4-tier strategy and plan using the expected yields from Barclay et al. Publication. But of course, right now we are very pleased to see that many of these expected planets are being converted into real planets. And so already right now, many of the TOIs, or in particular the confirmed TESS planets, are excellent targets, in particular for the tier 2, so for the full atmospheric characterization. So clearly TESS is very, very important for us. So let me just say a few key messages before leaving this presentation. TESS is really discovering planets and planetary systems that are absolutely optimal for ARIEL. And given that ARIEL really wants to push the atmospheric characterization to large statistical surveys or large population, clearly we want to have many planets to be able to observe their atmosphere and their chemical composition. But also ARIEL, the ARIEL policy, data policy will be extremely open. First of all, we are really welcoming the input and the feedback from the community already before launch through open workshop data challenges, and we're about to have publicly available some interactive websites for the targets and also for the some simulator, web interface simulator. But after launch, ARIEL will really offer a very open data policy, and many of the data from ARIEL will be available immediately to the community after quality control, so no proprietary period. And also between 5 and 10% of time available can be used for other science, and this time will be allocated through an open ESA call. Thank you very much for your attention, and thank you so much for giving this opportunity today to talk here.
All right, great. Thank you so much to all of you for your fantastic overviews of these incredible missions that we have coming up. So we have several questions coming in the chat already, and I encourage folks to continue to add questions as we go along. I wanted to start off first, sort of take moderator's privilege and also give people a chance to type more. So following a comment made earlier by Heike, what do each of you think would be the greatest scientific benefit of either overlapping operations or simultaneous observations even with the various current facilities and upcoming facilities? So what would be the greatest benefit between some combination of TESS, CHEOPS, Webb, PLATO, ARIEL of having simultaneous types of observations? And maybe we can start with Willy. I'll ask each of you in turn.
Yeah, I'm not sure there will be many opportunities for simultaneous observation between CHEOPS and ARIEL, or even CHEOPS and PLATO. Given the lifetime of CHEOPS, we probably will have our mission ending 2024, 2025, which is just when PLATO will be launched, and is still a few years short of the launch of ARIEL. But with JWST, certainly, and we have studied a system, TOI 178, with these 6 planet in Laplace resonances, and for studying further this system, we obtained JWST time. So there is a clear synergy between, there's a stepwise approach as usual, right? Is you discover these things, then you do the first characterization, and then you come with a large infrastructure. And at every time you have less and less, you have more and more pressure on getting the time. And so this is why sort of the broad spectrum of capability is so useful.
Okay, Heike?
Yeah, so we will certainly build on CHEOPS in that respect, because CHEOPS CHEOPS' goal is to get precise radii, and the CHEOPS targets in the PLATO field, of course, will get refined even further. So that is that's very useful, because people are, when I see the publications coming, and the publications in the queue, people are really addressing specific targets to a lot of physics. There's a lot of it's getting more and more in characteristics, and so I think that will come in very handy, and will build on CHEOPS. And for James Webb, of course, we hope that James Webb is operational so when PLATO launches, and then targets that we detect, which are a bit further out than what TESS has been done. If they are favorable around bright stars, of course, they would be ideal targets for James Webb spectroscopy. This is very clear. And the same is true for ARIEL. Here we talk about the larger planets, and they will go in ARIEL. And here, well, James Webb observing time is very expensive. So for sure, if you can get a 6-meter telescope and your target is difficult, you go for the, sorry, Giovanna, but you go for the 6-meter telescope. But the task that PLATO and ARIEL play is that we observe our targets, and we observe a large number of targets. So we will provide catalogs which have a pre-characterization. If James Webb is still operating after you have a few years of PLATO and ARIEL, then you can pick from these catalogs the best and most interesting targets, and there you have very good proposals for James Webb time and ELT times, yeah, or the gigantic telescopes on ground. So PLATO will give the statistical, yeah, and a large scale selection catalog, and that I think is a synergy that we play also with ARIEL for then the big dedicated investigations with James Webb and the big ground-based telescopes. That's how I see it. But maybe Giovanna has another point of view. Or...
Yeah, I was going to say, Susan or Giovanna, would you like to add? Susan, you can go first.
I think Willy and Heike have really highlighted the real synergy in exoplanets for sure, like in the sense that, you know, JWST time is expensive and hard to get. So, you know, the more you can get your list down to what is the best things to answer the key science questions, the better off we'll be to utilize that resource. And so I hope there is extensive overlap between JWST and these other missions to be able to do that. Also to hold on to the ephemerides, actually, so we can make sure JWST has could be efficient in its observing as well. I imagine, and though it's not less my expertise, that some of the same overlap would exist in like stellar astrophysics with those who are finding interesting objects that vary in different ways, that they will want to follow up with JWST in that same way. So I imagine, especially like from PLATO, that they will have that similar sense of a survey, and you'll find unusual things that you'll really want JWST to dig in on. So there's other people in this meeting who can comment on that way better than I could.
That's great. Giovanna, anything you wanted to add?
Yes, well, first of all, I agree with all what has been said. Of course, it's in the interest of everybody to make sure that we use all the facilities as much as we can, because they're all bringing in a slightly different perspective. And so perhaps synergies that I can think of that haven't been mentioned yet, synergy with PLATO on top, of course, of taking some of the targets from PLATO for atmospheric characterization. The astroseismology part of PLATO will also be very relevant to understand better the star and the stellar environment. So it's certainly in our interest as much as we can to make sure that among the targets, there are PLATO targets with this information. And I think with James Webb, of course, the synergy will be extremely, complementarity and synergy will be very strong. I show you just a very big strategy or plan, but in reality, we have multiple plans because we need to wait for the result from James Webb, because I'm sure that there will be so many new and expected results that we will have to revisit the plan when we have first results from James Webb. And that there is absolutely no doubt that if you want to go, for instance, for habitable worlds, then Webb is the way to go. ARIEL will stay mainly on the warm and hot planets, certainly if we're talking about small planets. So clearly in that case is a complementarity rather than synergy.
All right, excellent. So we have another, so we have several specific questions. Some of them have been answered already in the chat, but one question again for the panel was, what do you all see the role of smaller space missions like CHEOPS in the future of exoplanet science? So Webb, PLATO, ARIEL are all larger class missions, but we have these small sats like CHEOPS and other missions in development. So how do you see them playing a role in your mission? Anyone want to start? Oh, I think Giovanna raised her hand first.
I think they're great. I think we should consider having even more, not only because CHEOPS is an excellent example of how successful they can be, but having more a small satellite, it allows also to go a little bit more towards more curiosity, science, a sort of more exploratory type of observation than normally. The bigger is your telescope, the more constrained is the time, and so you can't really risk that much. And I think on the contrary, sometimes looking for something unexpected is extremely important scientifically. And I think also this small mission allows also to refine the science question and prop some parameter space that otherwise would be completely left untapped. And so I am personally a great fan of that. And so I think we should consider, in parallel to flagship mission and big mission, consider also smaller satellites.
Yeah, Heike, did you want to add to that? Or Susan or Willy? Yeah, go ahead.
So I fully agree with what Giovanna just said, and I just want to add that a single role for small missions would be, for example, to cover wavelength ranges that are not covered yet, like the UV. That would be great, and also the role of small missions to test technology that we need for larger missions. If you think about interferometry, iconographic missions, small missions can serve as a test bed to get the technology to the maturity we need to get the very, very large missions in the future.
Okay, Susan or Willy, would you like to add anything? I mean, Willy, you run a small mission, so how do you feel about it?
Yeah, I'm not going to advocate small missions, right? I mean, you know what I think, but no, I agree with that when everything what is said. I mean, I believe really we need a panel. You need a toolbox with more than one tool. You need tool adapted to every single things, and sort of a hierarchy where you can leverage the next step by using smaller things. It's just like same thing on the ground. You still have useful 2-meter telescope, 4-meter telescope, 8-meter, and possibly 30-meter telescopes. There is a palette of tools that you need, I think, to most efficiently use resources to study these exoplanets.
Okay, perfect. So looking at, so there's a lot of questions still coming in, but I want to jump to the newest one actually from Ben Monte. So currently at this conference, there are lots of early career scientists, undergrads, for example, who will be postdocs or junior faculty when PLATO and ARIEL are operating. So what is your advice, all of you, to students who are excited about new and upcoming missions? And what expertise do you see us missing in the field presently that you would recommend students work towards developing over the next few years to be ready to use all these facilities and make the most of their data? Susan.
So one thought I have for you is if you haven't gotten started with cloud computing, I highly recommend it. The data is only getting bigger and it's getting harder and harder to deal with. And so unfortunately, it's really fun actually, is, get used to not necessarily pulling all the data onto your computer, working on it and keeping your own little repository of things. All the test data is on AWS. And that will be true for Roman too, which is not part of this panel, but also related to exoplanets. I don't know what the plans of the other missions are, but JWST has thoughts of doing this, so there's no specific plans yet either. So think of that as a new way to work, and having those kind of skills, having those kind of computer skills, working with large data will help you as you go forward in your career.
Great. Any other thoughts on advice for students for any work on any missions, even developing a mission as a tangential question?
Maybe to be very concrete, of course, now when you work on test data, you prepare for PLATO, and the students who now work on test data and produce test data, they are perfect and have all the skills they need to work on PLATO data. So PLATO will provide calibrated light curves. It will also provide a catalog of results obtained. The majority of the PLATO data become public either immediately or after 1 year. There's lots of things to work on, and what you learn as a student now on TESS, you can directly apply to this data. So for me, the answer is very straightforward.
Okay, great. Any other thoughts before we move on? We have time for maybe a couple more questions.
Perhaps just to add, sorry, I'm interrupting you, Willy. Sorry, go ahead. I just wanted to say that I think they are a lucky generation because they have all this space vision and ground-based telescope of every size, and also delivering data for observation with different techniques, and so it's like different questions in the field of exoplanets. So I think it's great. They can really choose what kind of route they want to take in the exoplanetary science, and there is plenty of data already available, and these are excellent really for preparation for future observatories.
And Willy?
Yeah, I wanted to go in the same direction. I think the years to come are going to be really a bonanza year for data, new data of very high quality, spectra, photometry, RVs, and therefore we need people how to handle this, but also we need people with good ideas, new ideas, thinking out of the box, having clever ideas on what things mean, what to look for. I think this is what we will really need to handle all these new data.
Okay, great. So I think we'll wrap up with one more question. I'm going to paraphrase a question from Jesse Christensen. it was directed towards Giovanna, but I'm going to make it a little more general. So she said earlier in the week, we heard that TESS has found about 216 planets amenable to atmosphere characterization and expect to find maybe 250 more. So that leaves about 500 to get to 1,000. So in terms of ARIEL, do we already have enough planets given the ground-based surveys and tests and everything? And to also make it more broad, do we have enough planets to do all the things? You know, do we have enough planets for all your observatories to study, or what are we missing? How do we add more? I mean, we can start with Giovanna because that was directed towards you, but it'd be great to hear others.
Yes, of course. So of course we came up with this plan of going for about 1,000 planets because again, putting together the expected yields from TESS at the end of the mission, ground-based, PLATO, and Gaia, of course, that we haven't really yet seen all the data from astrometry. We believe that this number was actually very reasonable, and actually we're expecting about 2,000 planetary candidates being available in 2029. But even what is already there, so even if for whatever reason all these missions are stopped working or not working, the number of planets that are already available for atmospheric characterization is already huge, very diverse. So I would be extremely happy already with what we have. And so what it will come more, what is expecting more from our facilities will add to this. But I'm not worried about the number of planets because, again, TESS is not over yet. We have PLATO, we have ground-based facilities. So I think the problem probably will be to select the best planet, because even if 1,000 seems a big number, at the end of the day, we have probably so many to select from, which is a great problem to have.
All right. Yeah. Any other thoughts on the number of planets we have, you know, that are good for either atmosphere characterization? Do we need to do more, or do we just need to wait longer to discover more, to develop new ideas? Or sorry, Heike, were you gonna? Yeah, go ahead.
I unmute myself. Yeah, I think one, if we think not about observation, I fully agree with observations for Giovanna. There's so much to do, and I don't think we are short of planets, and we will have more planets than what we can do with the telescopes. But in terms of understanding the planets in a sense of physics and their characteristics, their nature, the correlation with the stellar type, the correlation with the age, the correlation with whether they are rocky, how much hydrogen they have in the atmosphere, do they have a magnetic field? And I mean, I can go on for half an hour and just name all the different factors that affect a planet, in particular a rocky planet, and all these new types that we have in between gaseous and rocky. And these factors are so many that we do need more planets, and we do need more well-characterized planets to understand that. In the moment, we are limited by the number of planets known and by the precision and information for the characterization. This is true, despite the fact that we have already more than 4,000 planets known. So we do need more planets, and I agree with Giovanna. We are not short of the need for observing time and ground-based observations for them, because some of the information can come from the ground.
Great, yeah, Willy or Susan? Sorry, you unmuted first.
No, I was just going to spin on that a bit. That I agree that what's probably missing is having enough in each of the diverse corners that Heike was talking about, so that you can really pick to those that will give you the highest signal to noise. I mean, like, at least for JWST, we're never going to be able to do a complete survey of exoplanets. There's just not enough time available. But hopefully we can get to the best ones where we can learn the most, so we can, you know, get to that next level and know what we need to dig into more to really understand the astrophysics and the physics and chemistry of these atmospheres and what that diversity really looks like. And so, you know, I was thinking, like, for instance, if you want to do transmission spectroscopy of a cool planet, you basically have one orbiting a white dwarf to choose from. So yes, we should try to find more in these kind of exotic corners of those various parameter spaces that we can go after.
Okay, Willy, any final thoughts for us?
Yeah, I think history has shown us that knowing a single planetary system in all detail is not enough to get the right picture, right? Exoplanet were needed for the statistic, for the diversity and things. And we are facing the same thing here. We will have to have a combination of sort of not too high resolution studies of a large number coupled with full detailed studies of a number of Rosetta Stone systems, if you want. And it's, again, this combination between the statistics and the individual most interesting cases that might help us to sort of better understand the whole subject.
Excellent. This is a great ending point, a great question. In the interest of time, we'll have to stop here, but thank you so much to the panelists for being here today. This was great. And I think with that, I hand it over to Avi or Andras.
Yeah. Thank you, Nicole. Thank you for the panelists. Before we go on the long break until the next session of the day, I want to present the honorable mentions for the posters. As we said yesterday, we're not going to do the usual competition where we have 1 or 2 winners, because there are way too many posters and we don't have the enough poster judges to do the thorough quantitative estimate of each poster. But we are doing an honorable mention of 9 posters. And to present those posters, I will share my screen and just walk you, or try to walk you through GatherTown. Let's see if this works. Okay, can you see my GatherTown? Can you see me on GatherTown?
Yes.
Okay. So actually, if you're on GatherTown, you can come and walk with me. We'll start from poster hall 1 and go through 9. So the order is somewhat arbitrary. So the first honorable mention is, okay, I think I got into the wrong room. Oh, this is room 1. Yeah, okay. This is a poster by Adina Feinstein. Right away, you see this is very well done visually. I think next time if I need to make a poster, I know who I want to help me. But the science here is also very interesting. Transmission spectroscopy, or trying to estimate the spin orbit alignment of a planet orbiting a young star. So we can also say it's a young planet using the H-alpha and calcium lines. Adina also prepared a website, so an interactive poster for this poster, so which you can go and look at. So this is the first one. Next, we go up to room number 2. Poster number, oh, there, I have a few followers. Poster number 224 by Emily Simpson. This poster is very self-explanatory. What the work here is attempting to look at the stellar variability period at the x-axis here in linear scale versus the orbital period from the transit on the y-axis in log scale. And systems that fall on the 1-to-1 line, those are suspicious, because usually we don't expect stellar variability at the orbital period. Okay, next one, we go to room 3. Okay, room 3, we go up, up, and up, and 316, it's a poster by Jake Clark. It's about using the information from the GALA survey, which is a spectroscopic survey, a stellar spectroscopic survey, in order to inform the understanding of planet candidates. What I really like about this poster, beyond the science, is that it takes you through a conversation. If you read the text, it's like a conversation or a short story. So it's very unconventional and very intriguing, and it's like you have to read until the end because you want to see what happens in the end. And there is also an interactive poster or a website for this poster where you can, where the plots are interactive. You can play with the zoom in and the scaling and so on. Next one, we go up and up to room 4, and from room 4 we go to room 5. Room 5, the entrance is here, and we go to 517. That is a poster by Sam Christensen, and they investigated the possibility of alignment or non-alignment between the inclination of transiting planet candidates and the inclination of the stellar binary system for transiting planet hosts that have a binary companion, a visual binary companion. Now, whether or not there is a correlation in the alignment, I will leave you to go to the poster and find out. Interesting thing about Sam Christian, he is a high school student, or at least he was a high school student, and he just graduated recently. So I don't know what your extracurricular activities were in high school, but doing astronomy in a professional level certainly wasn't one of mine. And I heard from a very credible source about 20 minutes ago that Sam Christian is coming to MIT for his undergrad. So good for Sam and very good for MIT. Next one. Yeah, I'm being blocked. We are in room number 6. And we are going to 611. This is a poster by Kao Samapon Tinyanonant. Obviously, I didn't pronounce it correctly, so apologies for that. This is a poster about a supernovae that was observed with TESS while it was exploding. So this is a TESS light curve. So this increase is the supernova itself. So it's very rare to catch a supernova like that. And also it is rare that you can trigger HST as a target of opportunity with HST to take a spectrum of this supernova like within 2 days after the explosion. And they learned a lot about the circumstellar environment, and HST observed this region, and it didn't find it. HST observed this region well before the supernova happened, but there is nothing there, so you can put an upper limit on the brightness of the progenitor of the supernova, and from there, eventually on the mass of the exploding star, and you can get some constraints on the mass of the progenitor. So this is a very, very detailed study of a supernova. Next, we go down here to 624. Whoops. This is, for some reason, it's not changing the. Sorry about that. Okay, let's try and move out of this room. I think GatherTown is playing tricks on me. I think what I will do is try to get out of GatherTown and get back in again. Okay, looks like this did the trick. Sorry about that. Next poster for an honorable mention by David Wilson. This is a mystery case. It's a white dwarf showing variability, photometric variability in TESS, but not only in TESS data. It's not completely clear what's going on. Things don't really, the different evidence, spectroscopic and photometric, don't really don't completely line up. So if you're interested in white dwarfs or interested in mystery cases, you'll find this poster very interesting. And we have 3 more to go. We go to room 7 and cross it all the way to room 8. And we go to 818. Poster by Nicola or Nikki Miller. This is a fresh or a modern approach to a classic thing that we can use eclipsing binaries to get very accurate stellar parameters. Here they are going after the effective temperature using test data and data from other surveys to try and get the effective temperatures of both stars in the binary system. They are analyzing more than one system, and I think this is supposed to be a series of papers that will be very interesting to read. And the last 2 are in room 9, 913, right at the entrance. Stellar quasi-periodic pulsations in highly active low mass stars. So studying activity by combining swift UV data and test data. So to get the UV and to get the optical or the red part of the optical with TESS to better study the activity. And this poster is by Teresa Monsu. And the number 9 and last is number 920 by Zach Claytor. This is machine learning. And if you haven't heard about machine learning, then I don't know where you've been over the last year or years. The poster walks you through the various steps of how to build a machine learning algorithm or a machine. And they are going here after detecting or measuring stellar rotation periods. Stellar rotation periods are useful for obvious reasons, but measuring them correctly is a non-trivial problem. And here, this is the machine learning approach to that problem. So these are the 9 honorable mention posters. The list of those 9 will be on the poster page on the website in a few minutes. In addition to that, I want to give a shout out to all the people who prepare interactive posters, and they are listed at the top of the list of posters on our poster page on the website. And you can click on them and it will take you to the website for the interactive poster where you see some animations or interactive plots where you can zoom in on the plot and change the scale right on the website. So this is it for the posters. So I can stop sharing. Now we will take a long break until the next session of the day. That will be, we'll start at 3:30 East Coast time, 7:30 UT, 9:30 p.m. Central European time. That will also be the last session of the week and of the conference. Now, one last thing, an idea that was proposed to me. Of course, we cannot have a group photo. Even if we all go on Zoom, there is way too many people that we're not going to be able to see anyone. What we want to try and do it virtually in the spirit of these days, and go to GatherTown. Those who want to, we can all go to GatherTown and be in the main room and huddle together. And in, let's say, in 6 minutes from now, that is 11:45 East Coast time, 3:45 UT and 5:45 Central European time, and 8:45 West Coast time, we can all be there together, and people can take their own screenshots. And you can feel free to post those on the random Slack channel. We'll see how it goes. So I've never done before, at least as far as I know. So if you want to join me on GatherTown for that, it's great. You don't have to, totally optional. And we'll see you on the next session later today. Thank you.